Okie dokie. We are looking at 8F2. Last question. It's a long one, but I thought if you could do this one, you've understood the topic pretty well. So it's about tokens in a washing machine. More specifically, the diameters of the tokens. They're normally distributed. Only tokens between 1.94 and 2.06 diameter will operate the machine. 2% of the tokens were too small, which would mean that they were smaller than this number. 3% were too big, which means that they are bigger than 2.06. I can represent this information in a little picture. So this is 8F2. We're doing question 10, last question. I think it will be probably the harder one to get through. We've got normal distribution. Now we don't know the mean or the standard deviation, but we do know that down at 1.96, there's a probability of 0.02 that we're smaller than that, and 0.03 that we're bigger than 2.06. And I think that's actually a 1.94. Right? So there's 95% of the probabilities in the middle, but we don't know exactly where the mean is, although I'm guessing it's pretty close to 2. I'll just check the numbers here. 1.94. Yeah, that's better. 2.06. We have to find the mean and standard deviation. Okay. Well, the way we can do this is with z-scores. So these are x's. Right, what we've got here is let x be diameter, centimeters. We know x is not distributed as normal, but we don't know the mean or the variance or the standard deviation. So we need to look at a z distribution, because with a z distribution we always know the mean and the standard deviation, right? Whoa, and we can start doing, sorry about that, that's awful, but we always know, if we go to z-scores, that the mean is 0 and the standard deviations are 1. I'm going to blame my dodgy pen for that odd bell shape. We've got the same 0.02. We can use inverse normal to find out this z-score here, up at what I'm about to call z2. Right, I could say 97% of the area, well, there's a 0.97 probability that we're below z2, and I could work out z2 as well. Right, so given that a z-score is your sample, particular sample, I'll just write an x, I think, minus the mean, divided by a standard deviation. Okay, we could say the probability that x was smaller than 1.94 was 0.02, and the probability that x is smaller than 2.06, well, that is 0.97, 100% minus that 3% there, and that means the probability of a particular z-score, it'll be negative down here, the z how can we write this, is smaller than 1.94 minus the mean on the standard deviation would equal this, right? And same as for the upper bound here, the z would have to be smaller than 2.06 minus the mean divided the standard deviation. But it's the same probability, right? I can use inverse norm, all right? So Z1, because with a z-score I always know the mean and the standard deviation. So given this probability, we could say Z1 equals inverse norm area mean standard deviation, Z2 inverse norm 0.97 mean standard deviation, and you'll be able to actually get z-scores. I can just fit this one on, I think, down the bottom. This one will be negative, this one will be positive. Approximately 2 standard deviations either side, I'd say. So, calculator time. Now, screen's a bit of a mess, but I think it'll be all right. So if we, I think we'll be able to see what we're doing. Just inverse norm. The first area is only 0.02, and I'm always going from the left. For those of you that have the older calculator, which only goes from the left. So that's minus 2.0537. 537, I can remember that. 2.0537. I want lots of decimal points because the standard deviation is going to be quite a small number. So I'm going to keep quite a lot of decimals as we go through. The next one, if we just copy the same thing but change that to a 97% or a 0.97 probability, we get our z-score 1.8808, rounding up. 1.8808. 1.8808. Okay, and we can use this magic formula. It's not magic, it's quite simple. We've discussed it in class. To now solve, all right, for mean and standard deviation. Basically, it's just simultaneous equations from here. So, we could write out equation 1 and equation 2. We can say Z1 equals 1 point, no it's not, minus 2.0537. Right, and that has to come from 1.94, isn't it? Yep, 1.94 minus some mean divided by some standard deviation, sigma. So therefore I could get an equation, I'm going to call it equation 1, do a bit of rearranging. We could say 1.94 equals, now let's times by standard deviation both sides, 537 times standard deviation. We could add the mean, and I could also set up an equation 2 that'll look quite similar. I know this Z2 was 1.8808. I know the formula. It's 2.06 minus the mean on the standard deviation. So we times standard deviation both sides. And we add the mean. We would get 2.06 equals 1.88. Now you don't have to do your simultaneous equations exactly how I'm doing it. I'm setting it up nicely for elimination because I can see these. I've got one mean in both equation 1 and 2, which I can eliminate nicely, and I can eliminate them with subtraction. Maybe I should have put that one on top so I didn't get negative numbers, but what ifs? Right, we've got a 0.6 and a 0.6 to the two. We've got a difference of 0.12 there. Here we're going to get minus 3 point something or other sigma, and these are just going to eliminate, right? So sigma would end up being this number divide whatever that number will be. Oh, made a mistake. It should be a 1, 2 divided by about 4, I'd say, or a bit under 4. I reckon it's 3.9, so let's actually work it out properly. So I need to do that number there minus that number there, and hopefully my calculator screen isn't too busy. There's going to be numbers all over it. I need to do that one minus that one. Okay, so we've got minus 2.0537 minus 1.8808. That equals minus 3.9345. 9345. Let's just write that in. 9345. That is almost 4, isn't it? So your standard deviation is going to be about that. Divide 4. It's going to be about this. But let me just check. Minus 0.12 minus 0.12 divided by that number's already minus, good. That number, we get 0.3049, rounding up, 305 as our standard deviation. 305. Now I'm going to need to make some room. I still haven't found the mean. What do you mean you haven't found the mean? I might do it up here actually, because we can just substitute in to find. Get sub our standard deviation into equation 1. So the mean would have to equal what? So 1.94. This is a minus here. It would now be plus 2.0537 times the standard deviation I've just found. And I'm guessing after all this work it's going to be pretty close to 2. But let's have a look. The screen is quite messy. Alright, so I'm trying to do this equation in here. Apologise for the mess. We're trying to do it all on one page. So 537 times 0.0305, and I get 2.00 rounding up 3. 2.003. And I'm going to keep my mean and my standard deviation, which I worked out there, for part 2 of this problem. What if I should leave that up? Let's just keep the, we now know the mean is 2.003 centimeters, and we know that the standard deviation, quite small, 0.0305 centimeters. Okay, that's part A. There we go. Next. Wrong button. Next. Find the probability that at most one token out of randomly selected sample 20 will not operate this machine. Will not operate. Well, what's the probability that a token won't operate the machine? I should have kept that picture up. Whoa, okay. 2% of the tokens are too small, 3% are too big. So the probability, if I said let y be number of tokens that don't operate a machine. Let's just say that don't work. That don't operate the machine. The p-value there will be 5% because that 2% are too small, that 3% are too big. So the probability, if I just took 1, the probability would be 0.05. However, we're taking 20 tokens, and we've got a binomial situation. Either a token works or it doesn't work. Right? The probability it doesn't work is 0.05. So y now has a binomial distribution. It's a binary system. It either works or it doesn't work. There's 20 tokens. So n is 20 and p is 0.05. Okay, now the question's asking about what's the probability that at most one token, at most one means this, right? You've got 20 tokens. The probability that none of them work, the probability that one of them doesn't work, the probability that 2 of them don't work, and so on, all the way up to what's the probability that all 20 don't work? Could be tiny. So we could look at this distribution, and we're interested in at most 1, which includes none of them. Let me just rephrase this. The number of tokens that don't work is at most 1. Let me just be careful in my wording here. We could have 0 tokens don't work, which would mean all of the tokens work, right? Or we could have 1 token doesn't work, which would mean 19 others would work. Okay. So really we've got a cumulative situation here. We need to account for none of them and 1 of them. So we need to go to binom CDF. Right. This probability, I could go binom cumulative density function 20 trials. Oop, that's supposed to be a 0. That's the probability. I want to know 1. Remember, if you let your value be 1, it includes the 1. And remember, this function in the calculator, binom CDF, always goes from the left up to whatever you've selected. Right? So this let's have a look. Second dist binom CDF. There we go. Trials, 20 tokens. There's only a 5% chance they don't work. I want to know about the 0 and also the 1. And I get 0.736. So what does that actually mean? I had to put this into words. 736. So the probability that what did they say? At most one token does not work is 73.6% or 0.736, right? So you've got a pretty good chance that 19 out of your 20 tokens will work. Okay, let's look at the last question. I know this is a big one. Last question. C. Jake has 3 tokens. Find the probability that they all have a diameter greater than 2. Now this is also binomial. I'm going to use Y again, rather than go to another letter of the alphabet. Let Y be number of tokens with diameter greater than 2 centimeters. Now, why is this binomial? Because you're either greater than 2 centimeters or you're not, right? And Y would be distributed as binomial. We've got 3 tokens. And we've got some p-value that who knows what it is, right? Let's draw a picture to find out. So we've got normal distribution, right? We know that the mean is 2.003. What's just looking at the probability that one token should be a bit close to the mean, really. I mean, all this area here is what I'm going for, because Jake's interested in tokens that are greater than, or I'm going to work out smaller than. I'm going to do everything from the left. Here, 2 centimeters, right? So I want to know what's the probability that my token is smaller than 2. Although maybe I should work out greater than 2. It's probably quicker and smarter to do it that way, isn't it? Yeah, let's do that. All right. Because this is a normal CDF and the old calculators don't have to work from the left. They can do it this way. So the mean is, there's your mean, but 2 is a bit lower than the mean, 2 centimeters. It's going to be a bit more than, oh, not that much. That's a terrible drawing, isn't it? I'm sure it's only just a bit bigger than 50%. Apologies for the drawing. We want to know what's the probability that we're just looking at one token and its diameter, probability that a token diameter, I'll just write diameter, is greater than 2. And we could work that out using normal CDF. Right, we could have a lower of 2. We could have an upper of super big, 1 times 10 to the 99. Mean, we'll need to put in the mean, and we need to put in the standard deviation, 0.0305, and we should get an answer that's just a bit bigger than 50. It's pretty close to 50, but with such a small standard deviation, I think I'm going to not just assume that it will be 50%. It'll be a bit bigger. So we're doing normal CDF now. Now lower is 2 centimeters. Upper is 1 times 10 to the 99. The mean was 2.003 and the standard deviation is 0.0305, and we get a percentage of 54%, or probability 0.539. Let's go for that. 0.539. 539. Okay. So now I can actually put a number in here. Right. So let's think about what Jake wants. Good old Jake. He wants all tokens. Let me just reread this. All tokens have a diameter greater than 2. It's got 3 tokens. Right, well, we could just do that number to the power of 3, couldn't we? We could think about, so coming from here, we could think about a situation, right? Let's draw this again. A binomial distribution. We could have 0 tokens greater than 2 centimeters diameter. We could have 1 token. We could have 2 tokens. We could have 3 tokens. Right? And he needs all of them, right? So you could work out binomial CDF for up to 2. You could do 1 minus binom CDF and subtract away those 3 columns. You could do binom PDF. I think I might do that. So the probability, let's write this, the probability that y is greater than or equal to 3, or just equal to 3 really. Yeah, let's just say equal to 3. Seems a bit silly saying greater than or equal to. Equals binom probability. So we're using the P, not the C. We've got 3. We've got our probability value now, 0.539. Now, I don't use this function much. Let's just check what goes in the calculator for this one. Binom PDF. There we are. Trials 3. P 0.539. X value 3. And we get 0.1565. Which isn't really that high, is it? 0.157, I think. So I was entering it right. Prox 0.157. Now, because we're looking at just this one situation, there's only one way to get all 3. There's only one path through the tree, if you imagine a tree diagram, and you could have simply just done this. So where can I write this? The probability that the number of tokens with diameter greater than 2 is 3 equals 0.539 to the power of 3. And let's just double check that for you. So 0.539 power of 3, and you get the same number. And I guess you could have also used binom CDF, but it seems a little bit overkill. 1 minus, that's a plus, I want a minus, can't see the buttons. Binom CDF. These should all give the same value, right? 3 trials, 0.539. This time I'm going to put in a 2, paste, and I get the same value again. So what I did, that last one, worked out what's the probability of getting 0 tokens, 1 token, and 2 tokens, and subtracted those away. Right, so the method doesn't matter too much, but you should probably show some working. Okay, I think that's about it. Thank you for watching.